Assalamualaikum warahmatullahi wabarakatuh. My name is Joshua from Electrical Engineering, and today I'm going to show everyone my presentation about grounding system. What first comes in mind is what is grounding system? IEEE defines grounding system as a system of electrical circuits that are connected to the ground that function when a leakage current can discharge electricity to the earth. The purposes of grounding system, there are two. The first one is to provide a path for a current flow that can provide detection of the occurrence of an undesired relationship between the system conductor and the earth. The second one is to limit the amount of voltage to the earth to be within the allowed limits. There are many requirements for a good grounding system. Those are limiting the definite values the voltage to earth of the entire electrical system, proper grounding of metallic enclosures and support structures that are part of the electrical system and may be contacted by the personnel. Protection against static electricity from friction, protection against direct lightning strokes, protection against induced lightning voltage, and lastly, providing good grounds for electric process control and communication circuit. Based on IEEE standard, there are 5 types of grounding system. The first one is TNS, TNCS, TT, TNC, and IT, which I will explain all of them one by one later. The first one is TNS. TNS, aka terrain neutral separate. In a TNS system, the neutral part of the electrical energy source is connected to the earth at one point, so that the neutral part of a consumer installation is directly connected to the neutral source of electricity. This type is suitable for installations that are close to electrical energy sources, such as large consumers who have one or more HV or LV transformers for their own needs, and if the installation or equipment is adjacent to the energy source or transformers. The second one is TNCS. In a TNCS system, or terrain neutral combined separate, it has a neutral channel from the main distribution equipment, which is power source, which connected to the earth and earthing at a certain distance along neutral channels leading to consumers, usually referred to as a PME, or you may know as protective multiple earthing. With this system, a neutral control can function to restore the earth fault current that might raise on the consumer side back to the power source. In this system, the installation of the equipment in the consumer only connects to the ground to the terminal provided by the power source. TT or double terre. In the TT system, the neutral part of the electricity source is not directly connected with neutral earthing on the consumer side. In TT system, consumer only must provide their own connection to the earth, namely by installing an earth electrode that is suitable for the installation. Next one is TNC. In the TNC system, the neutral channel of the main distribution equipment is connected directly to the consumer's neutral channel and the frame of the installed equipment. With this system, a neutral conductor is used as a protective conductor, and a combination of neutral and earthing side frames of the equipment is known as a conductor of PAN, or protective earthing and neutral. This system is not permitted for conductors less than 10 mm square or for portable equipment. This is because if a fault occurs, then at the same time as the PEN conductor carries the phase unbalanced current and the third level harmonic current, and it multiplies. To reduce the impact on the equipment and the living things around the equipment, then in the application of TNC system, the PEN conductor must be connected to a number of electrode rods for earthing on the installation. IT, isolated letter. The first letter, we know that I, T, in the system, IT system, neutral is isolated to the earth. The PE point is not connected to the neutral channel, but directly connecting to the earthing. In the second figure, we know that in its application, the neutral point of the IT system is not really isolated from the earth. It's still linked to the impedance, which has a very high value around 1000 until 3000 ohms. This serves the purpose of limiting the level of voltage overload when there is interference in the system. All of the types of grounding system has their own plus and minus. For example, the advantage of TT is safe and reliable, IT is continuity operation, and TNS is the safest. TNC is the cost advantage, and the TNCS is safety and cost. The safety itself from TT is very safe, IT is less safe, and TNS the safest, while the TNC least safe and safe. And the rest you can see as in the table. The equipment in grounding system, we have earth resistance tester. This is the instrument used to measuring the resistance of the earth, is known as the earth tester. All the equipment of the power system is connected to the earth through the earth electrode. The earth protects the equipment and personnel from the fault current. The resistance of the earth is very low. The fault current through the earth electrode passes through the earth. Thus, it protects the system from damage. There are two types of earth resistance tester, which is analog and digital. The first one we want to tell you is the analog. The analog grounding resistance tester is realized by four main blocks: DC generator, rectifier, current and potential coil. The deflection of the pointer of the analog screen depends on the ratio of the voltage of pressure coil to the current of the current coil. The next one is digital earth resistance tester. The digital grounding resistance tester, it is realized by digital electronic blocks as timers, voltage regulators, and digital display. The range are changed with the multi-turn trim pot. There are videos in explaining how it works.
System. The simplest way to measure soil resistivity is known as the Wenner method. This involves placing 4 equally spaced and inline electrodes into the ground. The 2 outer electrodes, called the current electrodes, inject current into the soil. The 2 inner electrodes, called the potential electrodes, measure voltage, which is then used to calculate soil resistance. In our example, we have spaced the electrodes 10 feet apart and 6 inches deep. For this test, we are using the AEMC Model 6471, a 4-pole ground resistance tester. The 2 outer electrodes are connected to the instrument's outer terminals. The inner electrodes are connected to the inner terminals. Let's pause a moment to discuss how these terminals are labeled. According to international standards, the current terminals are called H and E. Some manufacturers label these terminals Z and X, while others use C1 and C2. Similarly, international standards define the potential terminals as S and ES. On some instruments, these are labeled Y and XV, and on others, P1 and P2. In this video, we will refer to the current terminals as Z and X, and the potential terminals XV and Y. The Model 6471 has the capability to automatically calculate and display soil resistivity, a value represented by the symbol ρ. To measure this value, turn the dial to the ρ setting and enter the distance between electrodes, as instructed by the instrument's user manual. Then press the Start button to take a measurement. After a few moments, the resistivity reading appears. If you regularly need to perform soil resistivity testing, consider purchasing an instrument such as the Model 6471 that automatically calculates this value. This will save time and eliminate potential math errors. If your instrument doesn't offer automatic soil resistivity calculation, simply take a resistance reading. For example, if you don't enter the electrode distance, the ρ setting on the Model 6471 displays soil resistance, which as you can see is 15.1 ohms. We can now use this value to manually calculate the resistivity of the soil. The complete formula for soil resistivity is shown on the screen. However, a more simplified formula can be used when the auxiliary electrodes are driven to a depth of approximately 1/20th of the electrode spacing distance, as we've done in our demonstration. In this formula, soil resistivity equals 2 pi multiplied by A, the distance between the electrodes in meters, multiplied by R, the reading obtained during measurement. So to calculate soil resistivity, we multiply 2 pi, or 6.28, by 3.05 meters, the metric equivalent of 10 feet. We then multiply this by our reading of 15.1 ohms to obtain a soil resistivity value of 289 ohm meters. A grounding system typically consists of a grounding conductor, a bonding connector, its grounding electrode, typically a rod or grid system, and the soil in contact with the electrode. An electrode can be thought of as being surrounded by concentric shells of earth or soil, all the same thickness, with each successive shell having a larger cross-sectional value over which the resistance is distributed. Note that increasing the diameter of the grounding electrode does not significantly reduce its resistance. For instance, doubling the diameter reduces the resistance by less than 10%. However, driving the ground rod deeper into the earth does substantially reduce the resistance. As a general rule, doubling the depth to which the rod is driven into the ground reduces its resistance by up to 40%. However, this has its practical limits. When a ground rod is installed, it's essential to test its resistance to ensure it is functioning effectively. The 3-point follow potential test is a commonly accepted method for measuring the resistance of single grounding rod or grid systems. The diagram shown on the screen illustrates the internal circuitry of a standard follow potential tester. Packaged inside a typical instrument are two independent circuits. One circuit is a constant current generator, the other a high impedance voltmeter that measures the voltage drop and then calculates and displays resistance. By inserting auxiliary electrodes into the earth at certain distances from the electrode under test and then connecting them to the instrument, the operator sets up a bridge circuit within the earth. Current flows into the earth through auxiliary electrode Z and returns to its source through the rod under test. A voltage drop is developed between these points and is measured by the Y auxiliary electrode. By positioning the Y electrode at a number of different points between the rod under test and the Z electrode, measurements can be plotted and a characteristic curve becomes evident. In a full follow potential test, this involves taking a measurement at every 10% increment of the distance between the rod under test and Z. To ensure an accurate measurement, be sure to place the current electrode far enough from the ground rod under test so that the central measurements of the potential electrode will be outside the sphere of influence for both the ground rod and the current injecting electrode. The best way to determine whether or not the current injecting electrode is placed correctly is to perform a simplified type of follow potential test called a 62% test. This involves taking measurements at 52%, 62%, and 72% of the distance between the grounding rod and current injecting electrode. If the spheres of influence of the ground rod and current injecting electrode are in collision, readings taken at these points will vary considerably. When the ground rod and current injecting electrode are positioned correctly, readings will vary only slightly as measurements are made. To demonstrate, we will use the AEMC Model 3640 ground tester to perform a 62% test. Our test subject is an 8-foot ground rod. Before connecting the ground rod under test to the instrument, the rod must be disconnected and isolated from service. To measure our ground rod resistance, we connect the rod to the instrument's X terminal. We then place the current injecting electrode a minimum of 10 times the rod depth, or 80 feet, from the rod and connect it to the instrument's Z terminal. Finally, we place the potential measurement electrode at 62% of the distance from the rod to the current injecting electrode, connect it to the Y terminal, and take a measurement. We complete the test by taking measurements at 52% and 72% of the distance between the ground rod and current injecting electrode. As we noted earlier in this video, grounding systems can be grids consisting of multiple rods connected together. Grids are commonly designed for substations and similar facilities to provide the lowest possible earth resistance values, as well as to create an equipotential zone throughout the entire station. The fence surrounding the substation is usually included in this zone for safety reasons. Multiple rod grids are typically constructed with ground rods exothermically welded to copper mesh, creating a large area of zero potential earth when installed properly. When performing a follow potential test on a grid system, we cannot use the depth of a single rod to calculate the placement of the auxiliary electrodes. Instead, the distance should be based on the maximum inside diagonal dimension of the grid. In addition to single rods and grid systems, other design grounding options are available. These include grounding plates. These are typically thin copper plates buried in direct contact with the earth. Grounding plates are often placed under poles or similar structures. There are also concrete encased systems, often called UFRs within the industry. These can be one or more copper rods, rebar, wire, or mesh encased in concrete, often incorporated as part of the building's foundation. Also used are chemical rods consisting of a hollow electrode filled with electrolytic salts. This option can provide an efficient ground system in locations where poor soil conditions are present, and spacing for electrodes is limited. Chemical rods are often used in conjunction with soil enhancement materials that improve grounding effectiveness. These materials can also be used in other grounding systems located in soils with poor conductivity.
So that is the presentation from me. Thank you guys for your attention, and if you guys have question, let me know. Thank you.